Hi, welcome back to Fluid Mechanics. Today we're gonna solve this question. The velocity distribution for a certain flow in a pipe is given by velocity profile, which is equal to V max multiplied with 1 minus R squared over R naught squared, where R naught is the pipe radius as shown in the figure here. Determine the kinetic energy correction factor. So the question asks determine the kinetic energy correction factor, which is alpha. The formula of alpha is integration of velocity the power of 3 multiplied with dA cross-sectional area over average velocity the power of 3 multiplied with area. So the first step we need to find, in order to find the kinetic energy correction factor, we need to find the average velocity. So the average, which is the average velocity here, right? So by using the previous equation, which is the continuity equation, with respect to equation 4.10 under chapter 10, alright, we try to combine this equation. Step number 1, combine two equations to get average velocity. So what are the equations? So equation 1 is Q equal to integral of area, velocity and dA. This is equation 4 for 10. Under chapter 4, we refer to book Porter, Fluid Mechanics. And equation 2 is Q equal to A time velocity average. This is equation 4 for 10. So since the flow rate is the same, we can equate them together. Alright, we equate them. AB equal to integral of area Vn dA. So we move area to the other side. We finally become V average equal to 1 over A. Because area here is constant, we leave outside of the integral area velocity of n dA. Right? So in order to get the area, here, when we see this area, it is given that the small indefinite area dA equal to 2 pi r dr. So step number 2, given here is dA, which we're gonna replace here, is equal to 2 pi r dr. Okay, and then here velocity is changing with respect to area, in this case radius. So this velocity, what is the velocity change with respect to r? So we have this one, this term. Alright, Vr equal to, so we can replace this term with Vr equal to V max multiply 1 minus R squared over R naught. Okay, so substitute back into the equation. Step number 2, V average equal to 1 over area. The area in this case is the cross-sectional area, which is circle. We can use pi r naught squared. R naught is the radius here. Is the pipe radius, the total r. So we shall use the r naught. Integral of This is consider of velocity at radius. Velocity change with the function of radius. We replace this term V max 1 minus R squared over R naught. This is R naught is constant basically. And dA we replace with 2 pi R dr. So you can see that this is with respect to radius dr. Definitely we gonna integrate with respect to radius from 0 to R. R naught mean 0 from here. We gonna integrate from here until the R naught. So 0 to R naught. From this part, alright, we try to simplify the equation. Okay, this is constant. We move to the front, become, okay, this one is a pi. We can cancel pi, and we leave only 2. And this one V max is constant. We leave outside 2 V max, V maximum, over, this is R naught squared, integral of 0 to R naught 1 minus R squared over R naught. This is squared as well, dr. So this is as well as R. So we can actually multiply this with R inside. So we get here 2V max over R naught squared, integral of 0 to R naught, R minus R the power of 3 over R naught squared dr. So from here we can actually integrate directly. So integration become 2V max over R naught squared, integration of R plus 1 become 2 over 2 minus R, this plus 1, R4 over 4 R naught squared. This is not integration because this is with respect to constant from 0 to R naught. So you try to substitute the value of R naught inside this one. Definitely you will get the final answer is 1 over 2 V max. Right? So average velocity basically the half of V max. So from this part, we can find the kinetic energy correction factor under step number 3. Right, alpha equal to integral of V the power of 3 dA over average velocity 3 the power of 3 times area. So V3 we can replace as well with V of R equal to V max multiply with 1 minus R squared over R naught squared. So substitute this as well as dA, which is dA equal to 2 pi R dr, because we gonna integrate with respect to radius. So integration of 0 to R naught, V3 is referred to here. Okay, V3 is V3 max. We try to solve this one. Okay, or you can write like this. V3 bracket 1 minus R squared over R naught squared the power of 3, because you're going to replace this with the bracket. dA is equal to 2 pi r dr over with V average the power of 3, which is 1 over 2 V max the power of 3 time area, which is pi r naught squared. So try to simplify the first and the numerator and denominator. Alright, finally you will get 16 over r naught squared integral, because this one 2 the power of 3 is 18. Sorry, 2 the power of 3 is 8. 8 multiplied with 2, 16. Alright, becomes 16 r naught. Integral from 0 to r naught. Okay, this is simplified. 1 minus 3r squared over r naught squared plus 3r 4 over r naught 4 plus r 6 over r 6 naught dr. This one basically expansion from this term. Alright, this term we expand, and then we expand this bracket. This V3 max the power of 3. This also V3 max the power of 3. So we see the same term, we cancel out this. That's why there is no V max. After that, we can directly integrate. So we integrate them. 16 over r naught squared integration. This become r. Alright, this will become basically we have the r here. Right, we have the r here. So try to solve this one. We multiply r inside. Right, we will get integration of 0 to r naught, r minus 3r cube over r naught squared plus 3r 5 over r naught 4. Okay, and then this one plus r7 over r6 r naught 6 dr. So you integrate this one, definitely you will get 16 over r naught squared integration r squared over 2 minus 3r4 over 4r naught squared plus 3r6 over 6r naught 4 plus r8 over 8 r naught 6 integration from 0 to r naught. Alright, and finally you try to solve this one. Include substitute r with r naught, r with r naught, r with r naught, and finally you try to simplify the equation. You will get the final answer to be 2. Thus, the alpha, the kinetic energy correction factor is 2.